Hello everyone, this is a presentation that I presented in ICAART 2025, which title is Construction of Football Agents by Inverse Reinforcement Learning using Relative Positional Information among Players. Recently, advancements in reinforcement learning have made it possible to develop agents that autonomously emulate the behavior of human players. A football agent is one such example. Developing football agents that closely emulate their players is required. The football agent is trained via Google Search Football environment that considers physical phenomena. Realistic football agents can offer systematic simulation-based methods for addressing various tasks, including exploring diverse strategies and assessing the performance of actual football players. However, there is still a huge gap between the developed agents and their players. Let's take a look at the unnatural movements of the agents. In this case, the yellow team is aiming for the goal, but they are excessively crowding around the ball. These types of movements are common among beginners or people who don't know much about football. We think that these behaviors are caused by the fact that agents don't get appropriate reward for it. To bridge this gap, we propose a new reward called Relative Positional Reward. Our reward is based on relative relationships that the players actually observe, and it can be obtained from their players to incorporate the real player's mind. First, I will briefly explain the framework for developing agents using reinforcement learning in football agents. Reinforcement learning learns a policy that selects appropriate actions in each state based on rewards, and the reward for each future action is associated with the state. In general, the state is often represented by the position of the players and the ball and which team has the ball are given. The reward is given to the reinforcement learning model when the match is won or a goal is scored. The agent can take actions such as moving, shooting, and passing, including dribbling. However, unfortunately, there is a gap between the real environment and simulation environment. To close the gap between them, one method for bridging real data into this environment is proposed, and this method is called DQAS. DQAS closes the gap between the expert's actions in real data and agent actions in reinforcement learning by 3 steps. In the first step, an expert RL model is pre-trained on real data. In the second step, the data with states and actions are sampled in RL environment using expert model. Finally, the reinforcement learning model is trained on a mixture of sampled data and the real data. From what we have heard so far, you would think that it would be possible to get realistic agents, but in reality, there is a discrepancy. So we need to think about what causes this gap. We think the reason is the word and information that agents can observe. In the real games, the reward that is an advantage of actions and it's change all times and depend on the situation. Imagine a situation where a player passes the defender, then shoots and scores a goal. What makes you excited? It would probably be something like this diagram, you never feel a discrete surge of excitement. The other reason is information. In general, it is difficult to know all the information. Of course, legendary players that you imagine might be able to do that. However, normal players have relative information on the ground. For example, how far away from offense players from me, and so on. On the other hand, every agent in simulation has a complete bird view without ground level. It is certainly strange to be given absolute coordinates like these images. To close the gap, we propose a reward function that considers relative information starting from the player. For example, relative position or number of attackers or defenders nearby. Our purpose is to realize football agents that behave like their players. To this end, we propose a relative positional reward estimated by inverse reinforcement learning pre-trained on their data. This function takes the relative information as input, while reinforcement learning learns a policy for appropriate actions. Inverse reinforcement learning optimizes a reward function to enable learning the correct policy by using expert actions. In our approach, at first, we optimize a relative positional reward function by using real data. Then, without any sampling, the reinforcement learning model is solely trained on the sum of two rewards. One is the reward estimated from the relative state, and the other is basic reward. I will explain the outline of our methods to a single player. Reinforcement learning is usually done in this way, and our method is to add a new reward to it. There are two main steps to get a relative positional reward function. First, we calculate the expected value of state features from real data. These expected values are expert information and values are not changed. Then we optimize the weights of the reward function using inverse reinforcement learning while updating a policy by using reinforcement learning in a simulation environment. Once the reward function has been successfully learned, we solely trained on the reinforcement learning model. I will explain in detail the flow for optimizing the reward function. Relative positional reward function is a linear function of the product of weights and relative state features, and these weights are optimized using reinforcement learning. The basic idea is that an outstanding reward would be one that bridges the gap between two expected values of experts and agents in the same data. Expected values about agents is computed from sequence that agents act. Expected values about experts is preprocessed from sequence that their players act. The reward function is optimized so that the expected value of the agent state approaches that of the expert. Specifically, reinforcement learning is trained to maximize the calculated gain reward, and then the expected value of the agent state is computed from movements in simulated environment. The weight of the proposed function is the difference between the two expected values, and this process is repeated until this becomes sufficiently small. The list of relative features we defined is as follows. We utilize distance, angle, and proportion of players in a specific area. To speak about distance, we calculated the relative distance to the nth closest thing. Here, distance measures did not consider the actual relative distance, but also consider the gap with a general state, that is, the average distance of the real date. Moreover, I talk about proportion features. The proportion of players to the goal line is computed on this area. The proportion of players to the goal is used on triangle area. And the proportion of players who could pass is computed like this. We propose a basic reward that considers a position-weighted shot reward to improve the shot position. Weight of position is computed from real data, and weight values as a proportion of shooting for each position, 8 by 5. And this basic reward is shared for all methods. Other rewards are as follows. We explain the reinforcement learning methods, the evaluation matrix, the dataset, and the learning environments. We compare three reinforcement learning methods based on DDQN with the same basic reward. One is DQAS with real data. Others are DDQN and DDQN IRL with inverse response learning. DDQN IRL is a proposed method. For evaluation, we use two distribution distance between positions and actions based on callback library information that compute the distance to experts. The dataset composed from event data and tracking data from 95 J1 League matches, and we extracted sequence from receiving a pass to taking a shot. The data for training investment matching and DQAS are 102 goal sequence that takes a score. Data for training and testing reinforcement learning methods, we use these shoot sequences. As a simulation environment, we use Google Search Footballs players, 4 offensive players, and 8 defense players with goalkeeper. The scenario is offensive only. As a result of the experiment, we first show the position distribution distance and action distribution distance between the agents of each model and their players. The table shows the proposed method is superior to others and most similar to real players. Compared with DDQN, our proposed reward improves position and action distribution of all agents. From this now, I will introduce the results of detailed investigation about this result. At first, we check the shooting position of onboard agents. The table shows agent of DDQN and DDQN IRS takes a shot on the distance to the goal is more near to start position. DDQN is most similar to real players. The next is DDQN IRL. Agents of DDQN IRL have a tendency to take a shot as the most nearest position to the goal. It is a good result, not worse. When visualizing trace of sequences of onboard agents called blue, we can see the same tendency taking a shot nearby the goal. However, we investigate the relative distance between onboard agent and offboard agent to check whether the proposed reward can improve the relative relationships between agents. As a result, both methods using their data improve the relationships. The results are similar to their players. On the other hand, DDQN is not similar because it has the case the distance is too far. These mentioned results show DDQNIR improves the position appropriately. Next, we visualize action distribution of all agents, which is 11 dimensions. The diagram shows agents of DDQNIRs behave like real players. In aberration study, we consider the reward function of onboard agents and influence changing to the relative state. At first, the table shows the partial of the weights in the relative function. From the table, onboard agents are highly aware of goal. The negative values of the weights may be due to the risk. Negative weights are given to the proportion of enemies, so these results shows our onboard agents take apart from the defense players to take the shoot safety. It is in line with our expectation. We consider the influence the changing the computational states into relative states. The table shows the position distribution distance using two states. From the result, DQS works well on the absolute states except for the onboard agents. On the other hand, for our method, even if the state is absolute, IRL improves the position distribution distance. However, there was a tendency to shoot immediately by checking the agents. Finally, I summarize our purpose and contribution in this paper. Our purpose is to realize football agents behave like real players. We propose relative positional rewards using inverse reinforcement learning on real data and position-weighted shooting reward. Our method closes the gap positions and actions between agents and real players. Compared with conventional methods, our method gets the best result. Moreover, weights in the proposed function is in line with our expectation. In future work, we validate our relative position rewards and relative information states in full game scenario, not limited in shoot sequences, and needed to test not only offensive cases but also defensive cases. Thank you. That's all.